Hi. In this video, we're going to introduce linear functions of a complex variable. This discussion will be part of a larger discussion that will take place throughout the semester, in which we examine several special types of functions. Starting today, we'll be looking at linear functions and power functions, and the root functions, which are the inverses of the power functions. Later on in this chapter, although we won't cover it, one particular power function that is very important is the reciprocal function. This will be very important as you look later on in the text at chapters that are beyond where we expect to arrive during the semester. In future chapters that we will cover, we'll learn about exponential and logarithmic functions. We'll learn about power functions where your exponent is a complex number. And then we'll look at complex versions of the trigonometric and hyperbolic functions you may have run into. And then we'll look at inverses of those functions. In all of this, we're going to be looking at a couple common themes. Whenever we introduce one of these functions, we're going to be looking at how it behaves. We're going to be looking at the domain and the range of such a function. And we're going to be asking whether it has an inverse function and what that inverse function would look like, how it would behave. Well, starting today with the linear functions, which are the subject of this video, we want to introduce these by first identifying a couple actions that will be important in understanding linear functions. These actions are translations, rotations, and magnifications. And we'll go through each individually. Starting with translations. The effect of a translation is to take a point in the complex plane and shift it by a fixed amount in a fixed direction. Symbolically, what this looks like is when we take our complex variable z and we simply add another complex number to it. Now, calling that complex number b, what we'll see graphically is that the vector formed from the origin out to the point b in the complex plane will tell us how much and in which direction to shift every point of a region. So if I take a point z, I'm going to add that vector b, and the place where I end up will be the image under a translation. So translations shift points and regions along that direction that b determines. The next type of action is a rotation, which is exactly what it sounds like, with the understanding that the rotation always happens with respect to the origin. So we're going to imagine that every point is joined to the origin by a rigid rod, and we're going to just pivot or swivel that rod around the origin by a certain amount. Symbolically, rotations happen when you times a complex variable z by a complex number a, and that complex number a has modulus exactly equal to 1. Under those circumstances, the amount that you rotate everything by is determined by the argument of that complex number a. The third type of action is magnification. Magnification is a lengthening or shrinking of the modulus of a point by a fixed factor. Symbolically, this is what happens when you multiply a complex number z by a number a. This time the number a is a positive real number. So we're looking at multiplying z by a factor of 2 or a factor of 1/2 or something similar. Now the effect is to take the point z and imagine the vector from the origin out to it. We're going to lengthen that vector by whatever the factor a is. If the factor a is greater than 1, the effect will be an actual lengthening. If a is less than 1, but still positive, it will be, in effect, a shrinking of the modulus. In all of this, we don't change the argument, just the modulus. Talking now about linear mappings, or linear functions. Linear functions are exactly those that look like linear functions in your earlier algebra and calculus classes. We're simply going to take a number and times it onto our variable and add another fixed number. What's new here is that the a and the b that you multiply and add can be complex numbers. Now, to understand the effect of a linear mapping, we're going to take this expression and write it in a slightly different way. I'm going to factor out the modulus of a from the expression and then put a modulus of a in the denominator. Now, when we do that, you'll see that this is exactly equal to the previous expression. However, the number that is inside the parentheses multiplied onto z now has modulus exactly equal to 1. And we are then multiplying on the outside by a number which is real and which is not negative. And then we are adding a complex number. Now, all of these operations should ring a bell. We've just been discussing these. And we'll see that the effect of a linear mapping can be understood geometrically. We're going to think of taking a point z0, and then we're going to stick it into the function. Now, what happens to z0 first is that it is multiplied by this fraction, a over the modulus of a, which is a complex number with modulus 1. So the effect is to rotate it. Now, the argument of this number is the same as the argument of a, and that is the amount that we will be rotating z0 by about the origin. The next operation we would perform is a magnification, resulting from the multiplication of the modulus of a onto this quantity. Finally, we're going to be adding b, which has the effect of translating our most recent result by the vector b. As an example, or rather, before we get to an example, we'll note that because you are rotating and magnifying and translating, a linear mapping can't change the shape of a basic basic shape of a figure in the complex plane. It can move it away from the origin, it can move it around, it can change the size of it, but the basic shape will stay the same. To see an example, let's take a problem that you would have run into earlier in Chapter 2. We're going to find the image of the vertical line x equals 2 under the map f of z given there. Now, earlier in the chapter, what you would have done to solve this problem is to parameterize this set, the vertical line. Here's an example of a parameterization. You can feed the parameterization into the function and get out a parameterization of the resulting image in the W plane. However, now that we understand that this function is actually just a linear mapping, we can geometrically figure out what the image should look like. Now, here are the steps that we just talked about, geometric steps for applying a linear mapping. If we apply them to our function here, we'll see that applying f to a point z0 has the effect of rotating z0 by pi-fourths about the origin. Keep in mind that just like always, our arguments are measured in a counterclockwise fashion. We're going to take our point and then scale its modulus by a factor of root 2, because that is the modulus of our coefficient there. We're going to take the result and then add 2 to it, which has the effect of translating it by 2. Now, since 2 is a real number, we're going to be moving our point 2 units to the right. Now, when we perform this on every point on the vertical line, the result is a line that lies in a slanted manner in the complex plane. Now, to follow this through with a single point, we'll take a look at this point. Following those steps, we would rotate this point around the origin by an angle of pi-fourths. We would then magnify the result. We're going to change its modulus by a factor of square root of 2, so it will move farther away from the origin. And then we're going to translate it 2 units to the right. So our point that started out on the x-axis would end up about here. And you can see that that's what happens in the image. All right, so those are the basics of linear functions. If you have questions, please talk to me in class or leave a comment below. Thanks.